Saxon's Calculus Lesson 35 is the constant multiple rule, the derivatives of sums and differences, and then alternative notation. So what they're trying to do in part A is how do you deal with finding the derivative of a constant? Now, we learned before in an earlier lesson that all we have is a number that the derivative is 0 because you just had a constant. In this one, they want to know what is happening when you have a number in front of, or a coefficient in front of your variable, and how do we derive that? Now, they go into this rule, which basically says the derivative of the product of a constant and a function equals the product of the constant and the derivative of the function. So they say separate it into two pieces. And so they're basically, in the formula, they tell you d over dx for c f of x. So c is the constant multiplying with whatever the function is, that you're going to do c and then derive the f of x part and multiply them together. Now, they then at the bottom of 184 show you how that works with the formula, which we no longer want to use because we have the shortcut. And so I say, rather than go through all of this, basically you're just going to solve this with the shortcut, just knowing that when you bring this 2 down, it multiplies with this. Great. 2 times 2 is 4. X to the 2 minus 1 is 1. Oh, look, there's the derivative. So it's not really something that you have to think about the formulas for, you just do. So in example 1, it gives you f of x equals 20x cubed. And it says derive that. So 3 is coming down. So 3 times 20 is 60. And 3 minus 1 is 2. 60x squared is the derivative. Not hard. Example 2, find f prime of x, so the derivative, and g prime of x. So for the first one, f of x is 3x to the root 2. Okay, so this root 2 is going to multiply with this 3, and then x is going to have the root 2 minus 1. Now, I might be able to put that together in a decimal, but I don't need to overthink it. I'm just going to box that as my derivative. Then they wanted g prime of x when g of x was negative 14, x to the negative 5th. So we're going to multiply negative 5 times negative 14 and get 70. X to the, and then minus another 1 is negative 6. There's the derivative. Part B says the derivatives for sums and differences. So now it's asking what happens when I have one of these plus something else. And again, they go through the formula and they say if you are d over dx is how they put it in here, with f plus g, your answer is the derivative of, and it looks wordy, but they're simple, the derivative of f of x, so find the derivative of this piece and then add it with the derivative of the other piece. So just derive, and then follow whatever the sign is. So they give you another formula with the minus, and obviously they just change that to a minus. So you get the idea. Example 3, find the derivative if y equals 4x to the negative 3 minus 2x to the root 2 plus 4, and then they want us to derive. So we're going to do each individual piece. And since this was a dy, we'll put our answer in dy over dx. So we're showing that we're deriving a y value. Negative 3 times 4 is negative 12. Negative 4th when I subtract 1 more. Minus 2 multiplying with the root 2, and then x with, again, as we did before, root 2 minus 1. And, oh, the 4. So when I go to derive the constant, we remember that they drop off. And I'm going to just go through this one time to remind you as to why that worked. This would imply an x to the 0 sitting here because anything to the 0 is 1, and 1 times 4 is still 4, so that's what's making it the constant. And if I take 0 times anything, I get 0. So it's dropping off at that point. And that's why this is the derivative answer. We just did each individual piece. Example 4. Find the f prime of x, so derive, when it's 3x to the 4th minus 2x pi plus 2 over x to the negative 2 plus 4. So technically I should be saying f prime of x equals, and then I should be doing the derivative. So this one is 3x to the 4th. Now that's in a fraction form, so let's fix that to say 3x to the negative 4th. If I bring it up, I change its sign. So then that's negative 12x to the negative 5th minus 2 multiplying with the pi, and x to the pi minus 1 plus, and again I have a problem here, so this is going to be written as 2x squared when I move it to the top. So this becomes 4x minus 1 is 1, so I don't need that. And then the plus 4 is a constant that drops off. So that should technically be at the end. You just understand that I ran out of room there slightly. And then example 5, s is negative 16 t squared plus 42t, and find ds over dt. So ds over dt equals, I just didn't write the s equals originally. All right, but we want to derive it. So 2 times negative 16 is negative 32, t, 2 minus 1 is 1, and then plus, and then again, this implies a 1, so 1 times 42 is 42, and when I do 1 minus 1, that's 0. T to the 0 is 1. 1 times 42 is 42. So basically, if I have just a single variable, you're going to drop to the number when you derive it. And now part C, alternative notation. So they go back to the original equation with your f of x plus change in x minus f of x all over change in x. And I was trying to darken that side and I missed. And then they say, okay, we got tired of, as mathematicians, most definitely, of writing this change in x every time, so we decided to substitute an h in there instead, so that now we're reading it as f of x plus h minus f of x all over h, and that is the same format as that. And then they go through manipulating this and saying what happens when I take the limit of h to 0. And so if you're trying to follow what they're doing here, they get to a point where they're like, all of this lovely negativeness is up here in the numerator, and so we want to get rid of some of it if we can. And so normally when we have our negative things in our denominator, we change the sign down here and we multiply the same thing top and bottom because that equals 1. Well, they're doing it in reverse here, and they're saying, well, change it to a positive here and multiply the same thing top and bottom and manipulate it. And they ended up canceling out the h, which is why they did it that way, because it created that h up here. But unfortunately, all the nasty negativeness is now down here where we had a plain little h. So we end up with negative, well, not really negative. We end up with the messy stuff down here in the bottom, and the top has dropped to being a 1, which is what they wanted to do when they changed the sign, and then things just canceled off. Okay, well, that's nice. Then they plugged in the fact that h was going to 0 in the limit, and that took them down to, I'm kind of running out of space, but I'm going to put it over here. It took them down to 1 over 2 root x. Now, if you want to follow everything that they did on page 186 to the top of 187, that's how they manipulated it to here based on what I said with that weird thing where they changed the sign and ended up with the mess down here in the denominator. Okay, and when you simplify that, you get basically 1/2 x to the negative 1/2. because this was in the bottom, its exponent became negative, and its exponent was an implied 1, and its root number is a 2, so numerator and denominator. Now, what happens if I took that original, where's the equation they started with? Oh, where it was the f of x, they were using square root of x. That's it. They were using square root of x. Okay. So if I start with square root of x and I put that in its exponent format, that's x to the 1/2. And if I ask you to derive that using the shortcut, you get 1/2 with x to the, and then you've minused 1, so that's negative 1/2. Oh, look, that's the same thing I got when they went through all of their craziness on the bottom of 186. So my deriving the shortcut, if I'm plugging in the square root of x, that's what they did to get there. They proved it to you the long way, but the derivative still works with that. Then they do a part D here, in which they say, let's do the proof of the derivative of a sum. Well, we know from having just done all of these examples with the pluses and the minuses that basically when I derived, I just needed to do the shortcut derivative and it worked out beautifully. I can, if you so choose, to go through the derivative formula this way and plug in each individual piece and do it and discover that I get the same thing by doing the shortcut. You can go through that if you want. It's just kind of, I feel, redundant.